Hello guys, today we're going to be doing further mathematics, the paper 4-3 of May-June series of 2020, the further statistics. So before we attempt this paper, the few things that we need is pen and paper and the list of formulae MF19. Besides that, that's all we need and we can start this. Okay, so first question. Young children are learning to read using two different reading schemes A and B. The standards achieved are measured against national average standard achieved and classified as above average, average or below average. For two randomly chosen groups of young children, the numbers in each category are shown in the table. Test at the 5% significance level whether the standard achieved is independent of the reading scheme used. Okay, so I'm going to go about how the newer papers would want it. So first we need to write our null hypothesis. Right, and that is the standard achieved is independent of the reading scheme used. This is our null hypothesis. Okay, and this needs to be specified in the newer papers. This paper maybe not though. And the alternative hypothesis would state the exact opposite. So we can write hypothesis, null hypothesis is represented with h and a 0. H1 is going to be an alternative hypothesis. Okay, so we have to write like this. Okay, the second step is to calculate whenever we have a chi-square test tables, then we have to calculate the row and column totals. So how do we do this? Well, just why do we do this actually? It's because we need to find the expected values. So I'll come to that just in a minute. So let's first calculate the row totals. 31 plus 35 plus 22, which is 88. So let's put that 88 there. And then the second row total is 19 plus 50 plus 43, which is equal to 112. Right, so these are our row totals. What about column totals? The first one was 31 plus 19, which is 50. Second one is 35 plus 80 plus 50, so it's 85. And finally this one's going to be a total of 65. So now we have a column totals, we have our row totals. What's remaining is now our grand total, and this is particularly important. It's mainly due to the fact that it's being used in our expected value formula. So I'm going to write the grand total here. Total equals to 200. Okay, so total is 200. This total represents all the data over here added up. Okay, next we need to find the expected value. Before that, I'm going to use a symbol for this, and I'm going to write before we calculate the expected values for each, I'm going to denote each cell with a number. Given that we have 6 cells containing data, we're going to denote them with numbers 1 to 6. So this will be 1, this is 2, this is 3, the 19th will be 4, 50 is 5, and 43 is 6. I'll be denoting each of these as labels. We're not going to represent them as variables. Okay, next up we need to use the formula to find the expected values. So when I say E1, what does this mean? Well, it means that I'm trying to find the expected value for the first one, which is 31 here, expected value. This is the observed value. This is what we call O1. This is O1. To find E1, we have a formula. That is, I'm going to denote it right here. Okay, so E of I equals to the corresponding row total RT I times the column total actually wait, the RT, the I won't come here, just the corresponding row total and corresponding column total. And this row and column total, when you multiply it together, you have to divide it with our grand total, which is 200 in this case. And this is the formula that's used to calculate the expected value for every single chi-square test. So when we plug in these values in our calculator, for the first one our row total is 88. Second one, the column total is 50, and our grand total is 200. So our expected value is 22. Similarly, we can do this for all 6 values, and we gotta have to do this because these expected values are used in a different formula that's going to calculate the test statistic. So for this one, the row total remains the same, which is 88, but the column total is now 85. So we get a total of 37.4 for the second expected value. Moving on, we have the third cell in the row, which is having a column total of 65. So let's put that there, and we get 28.6. Fine. Now let's move on. Let's go to E4. E4. Expected value of the fourth one. Now we can see we're moving to a different row. So now we need to change our row total to 112. And our column total can be 50. So our expected value for the fourth one is actually 28. Okay, then we have expected for the fifth one, same row total as before, except this time the column total is back to 85 and the expected value is 47.6. The next expected value, which is E6, the final expected value that we had to calculate will come out to be the column total is 65 now and row total is 112. It will come out to be 36.4. Right. So now we've calculated all the expected values. We need to use another formula to calculate the test statistic. I will note the test statistic in the in T as T. Okay, and T is equal to the summation of it's going to T is equal to sum of when you have a sample size of n, I will always be equal to 1 in this case, and get observed value minus expected value of the same cell. We find the difference between the observed and expected, we whole square that difference, and then we divide it with our expected value again. And this is the formula that's used. So we do this until I equals to n being the sample size of, in this case, 6. 1 2 3 4 5 6. So we do this for each of them, and when what O represents over here is the observed value. So when I say O2, it means 35 because that's the observed value in the second table. So when I say E2, it means the expected value of 2, which is 37.4. Like this, we need to substitute for each and every one of them. So yeah, now that we have that, we can calculate when I equals to 1. When I equals 1, we have here our observed value O1 is 31, expected is 22. We square the difference, whole divided by 22. This is what happens when I is equal to 1, right? And now that we have the summation, right, that means we need to add it. And now when I equals to 2, we need to do this until I equals to 6. So over here, before I put values in here, let me just put this in the calculator. 31 minus 22 the whole squared, whole divided by 22, and I don't put equal to just yet because I want to add up all of them. So next up we have when I equals 2, it will be O2 minus E2 whole squared by E2. So O2 being 35, 35 minus 37.4 whole squared by 37.4, and this will give us our second part for when I equals to 3. I equals 3. So now we have when I equals 3, It is going to be the expected observed value of 22 minus the expected of 28.6 whole square, the difference, whole divided by expected value 28.6. This is added on when I equals to 4. I equals 4. When I write I equals 1, 2, 3, 4, this isn't necessary. In fact, you don't even need to mention the formula, but this is just an easier way of understanding what we are doing, right? So let's just put these in the calculator first. 35 minus 37.4 the whole square whole divided by 37.4. Okay, next we have here 22 minus 28.6 whole squared whole divided by 28.6. Next we have when I equals 4, it's 04, which is 19. 19 minus expected of 28 whole square, the difference, whole divided by 28. It's a simple procedure, but it's just a little time consuming, and you can be quite error prone to this given its repetition. So I equals 5 now, and we have to add it with, so this is added on. When I equals to 5, our observed value becomes 50. Our expected is a 47.6. Whole square, the difference, whole divided by 47.6. Right. Let's put these two in the calculator, and then we will be doing for the last one. So 19 minus 28 whole squared by 28 plus 50 minus 47.6 whole squared divided by 47.6. Right. And the final one, when I equals to 6. So when I equals 6, we can write here. Yeah, so when I equals 6, the observed value is 43. Expected is 36.4. Find the difference between the observed and expected, whole square that difference, and divide it with our expected value. And this right here is going to fetch you another mark, writing all this. Once again, I specify you don't need to write down about the entire summation formula or I equals 1, 2, 3. This is just for understanding. And now we can calculate our test statistic given that we have all this. Let's plug this into the calculator and we can find out the values. 43 minus 36.4 whole squared whole divided by 36.4, which is equal to 9.56947. Now whenever we get a test statistic value, I'd like to keep it to 4 significant figures, and the reason why is because in the list of formula, which is MF19, you will see that each of the values in the chi-square distribution and inferential statistics always include in 4 significant figures. I will just prove it to you right now. These are 4 significant figures, and well, these areas are 4 significant figures. Some of these aren't. Yeah, okay. Yeah, like all of this is 4 significant figures. So now let's move on. Now that we have a test statistic, what do we do next? Well, that is to find the critical value. Whenever we are performing a test, we need 2 things: test statistic and critical value at the 5% significance level. Okay. Now how do we find the critical value in a chi-square distribution test? We go to the chart and you can see that there's a column heading of P and a row heading of nu, which is a Greek letter nu, and that represents degrees of freedom. Okay, so now we need to find P and we need to find the degree of freedom, and once we find the degree of freedom and p, we can find the intersection and then we can match it to the corresponding critical value. How do we find p and nu? So first of all, we'll find p, and that is a little bit more harder than finding the degrees of freedom, but it's quite simple. So p is equal to 1 minus alpha by 100. Okay, so whenever we have a chi-square test, alpha always represents this value over here, the number value you get. If you want, we can consider the entire 5% and then we can modify our equation to 1 minus alpha, but just for easier purposes we can put alpha equals 5, and therefore p equals to 0.95. Okay, so now that we found our column heading, we know that our critical value is somewhere here. Now to find our degree of freedom, this is the rather more simpler part. So degree of freedom is in a chi-square distribution test where you have rows and columns is going to be the number of rows minus 1 multiplied by the number of columns minus 1. In this case you have 2 rows and you have 3 columns. Just to testify again, yeah, 2 rows 3 columns. Using this you can see that it's going to be 1 times 2, which is equal to 2. Now we have a degree of freedom and p. So at degree of freedom 2 and 0.95, you can see our critical value is 5.991. So let's put here, okay, how do we reference that the critical value is this? So there is a way to do this. It's so we write here, draw a straight line like this. Okay, and this is called the chi-square, right? And now we need to write our degree of freedom over here, which is 2, and now we need to write in brackets our value of p, which is 0.95. This is what you call referencing the critical value, and although this may not give a mark, it's good to specify this in case of any kind of misunderstandings. And you have here 5.991. Now we are coming to the final parts. Now we have to compare our critical value and our test statistic. So 9.569 and 5.991. Now using comparison operators, is the test statistic greater than, equal than, or lesser than the critical value? You can see that it is greater than, and whenever the test statistic is greater than, we always reject H null. If it were lesser than, then we accept H null. So in this case we have to write reject H null, reject H null, and our conclusion will be, whenever we reject H null, we write sufficient, or there is sufficient evidence to suggest that standard achieved is dependent on reading scheme used, or reading scheme. Yeah, reading scheme used. Fine. This is how we write our conclusion, and that is all there is for the chi-square test. Yeah, let's move on to the inferential statistics, confidence intervals. Right, so for confidence interval there is a formula that is CI, representing confidence interval, equals to sample mean of x minus sample mean of y plus or minus. Now over here we can write z or t, and this is going to be multiplied with our unbiased estimator. So how do we do this? Are we going to use the z value or the t value? So when we are writing down this formula, we have to write zs or we have to write ts, right? Zs meaning z multiplied by the root of our unbiased estimator, the combined estimator. So how do we use the t value or the z value? It's very simple now. We have a total of 40 observations from x and 50 from y. So when you combine the degrees of freedom, we get 40 plus 50 minus 2, which is 88. Now when we go to the t distribution, you can see that there is no degree of freedom for 88 that they're giving critical values. Hence, we have to refer to these values here. And these values are the z values. We're going to use these values as a critical value. Hence, we're going to write z, zs. S meaning the unbiased estimator rooted. But an easier way of writing this so that we can directly plug in our values would be like this. Okay, now that we have our formula, now we need to identify what values are missing and what values we can plug in to get our formula. So we have mean x minus mean y, that is 24.4 minus 17.2, which is 7.2. What we don't have is z and s2. So how do we find the z and s2 values? Firstly, let's take note of the number of samples we have. So number of samples for x equals to 40. Number of samples for y equals to 50. Now there is a formula to calculate s2, which we have to use here. So s2 s2 is equal to s2 of x whole divided by nx, s2x being the unbiased estimate for x and nx being the number of terms for x. This is added on with s2 of y whole divided by number of terms of y. And the reason we don't use the S2P, which is pooled estimate, is because it says that the unbiased estimates for the population variances are as follows. Nowhere does it mention that the population variances of x and y are equal. If they were equal, then we use the pooled variance formula. In this case, we should not, because the variances are not assumed to be equal. And now we can just plug in our values. So over here we have S2x, which is 10.2. We divide that with our number of terms of x, which is 40. We add that with S2y, which is 11.1, divide that with 50, and we get our unbiased estimator as 0.477. And this is our S2 value. Now we need to calculate Z. So to do that, we have Z. I'm going to write down the entire thing. So the only thing we need in Z is the value of P. That means that P equals to, and for confidence intervals or two-tailed tests, we always have this formula over here. So that is 1 by 2 times 1 minus alpha over 100 plus alpha over 100. That's just a simple formula, but once you get enough practice with the confidence intervals, you will realize that in the confidence interval, which is 0.90 and to 1, we just need to find the midpoint of it, which is 0.95. But when you have here alpha equals to 90, if you plug in the values of the formula, you will still get the same result. This formula is just mainly used to help out and guide those who don't understand how to get our CI values. So here we can plug in, we get our value 0.95. That is our P value, and so our Z value equals to is going to be 0.95 column heading, so Z value is 1.645. Now that we have every single value we need to calculate the confidence interval, we can just plug that in. So going back, CI equals to 7.2 plus or minus 1.645 root of 0.477. Okay, now let's calculate 7.2 plus or minus. Let's calculate this. 1.645 times root of 0.477 is equal to 1.136. Is equal to 1.136, right? And now there is a simple thing that we need to use. So in the format of negative comma positive, what I mean by doing this is that our confidence interval should stay in this format. So it doesn't mean that this value should be negative. It should mean that we do 7.2 minus. We do in the plus or minus operations, we do minus first. When we do minus, you get your first value. When you do plus, you get your second value. That's how confidence intervals work. You don't do plus first and then put that in this spot. So let's perform 7.2 minus this value. Minus this gives you 6.06. That is going to, so our confidence interval equals to 6.06. Keep it to 3 significant figures because it's the final answer. In calculations, we keep it to 4. And to find the when you add it with this, you get 7.2 plus 1.136 is 8.336. So we can significant figures of 3, we can put it to 8.34. And that is our confidence interval. Yes, and now we can move on to continuous random variables. Right, so for this one, this question, we can label up our equations 1 and 2. So the first is 1 by 5x for ranges of 0 to 2. Next one is 2 by 15, 5 minus x, ranges from 2 to 5. Find the CDF of x. Okay, so given that our range is from 0 to 2, we will have a simple integration step. So let's do for the first one, which is, we'll take this. First one as the integral of 1 by 5 of x. So let's write 1 by 5 outside the integration. Zoom this in a bit. Yeah, 1 by 5 integral with limits. Now whenever we integrate to find CDF, we replace our upper limit with x. So 1 by 5 times x, and our lower limit is 0. Okay, and the integral that we need to do, what we need to integrate is x, right? But in this case, since our upper limit is x, we can't have x here, so we need to integrate a dummy variable which I call t. Any variable is fine, but the most commonly used is t, and so dt is what we're going to be differentiating with respect to. When you do this, you get 1 by 5, and now let's integrate t. Integration of t is 1 by 2t squared. So let's write here 1 by 2 t squared with upper limit as x, lower limit as 0. And so now we can put as 1 by 5 times 1 by 2. Now we need to plug in our upper limit. When you plug in our upper limit to the dummy variable t, we can put 1 by 2 x squared. And this is subtracted from when you plug in your lower limit into t, which is going to be 0. So we can just close the bracket there and then. And now we can simplify our entire equation to get x squared times 1 by 10. So that's our first CDF. Our second one though won't be as simple. And the reason so being that we need to include f2. So if small f represents PDF, the larger f equals to the CDF. PDF being probability density function, fx, and the capital F of x represents the CDF. So this is quite important to notice. So when I put f, we take 2. The reason we take 2 is because it's the upper limit of the first equation and the lower limit of the second equation. So we put f of 2, and even though the inequality says that the x must be lesser than 2, we can still plug this in our equation. So f2 plus, now we need to integrate this formula right here. To integrate that formula right here, we can factorize our 2 by 15 outside. So 2 by 15 goes out. Let's integrate. Upper limit is going to be replaced by x just as the previous one. Our lower limit, however, will not be replaced. It's going to be 2. And in the brackets, we have to write 5 minus x. Okay, but once again, x cannot be here because we're having an upper limit of x. So we're going to put here t. And we're going to differentiate with respect to t because that is the variable we have here. So when we differentiate, first of all, let's do integrate, by the way. And first of all, let's do f of 2. When you plug in the value of 2 into this function here, the CDF function here, you get 2 squared over 10, which is just 4 by 10 or 2 by 5. And this 2 by 5 is added with 2 by 15 times. Now we have to integrate with 5t minus t squared over 2, t squared over 2. With limits of being x and 2. Right. Now let's make okay, now let's simplify this. 2 by 15, no wait, 2 by 5. So 2 by 5 is added on with, now let's multiply 2 inside this bracket, right? When you include constants inside the limit bracket, it won't affect the entire formula. So let's just put 2 times this so that we can get rid of the fractional 2 here. So we get 1 by 15 times 10t minus t squared with limits x and 2. And we can simplify this further by putting 2 by 5 plus 1 by 15. Now let's put in our upper limit value, that is x. So we get 10x minus x squared, and over here we have 20. So it's going to be, now we need to subtract. When you put in 2 into our lower limit, we get 20 and minus 2 squared, which is 4. Now we can further get the values. So 2 by 5 plus 1 by 15 times, multiply this with 10x minus x squared. So inside the bracket we get a positive 16, but given that negative is in outside, we have to get negative 16 here. And while this is the correct answer, we can simplify this even further, right? So we can put 2 by 5 here, this stays there, plus 1 by 15, and right here 10x minus x squared, and we close bracket because now we are multiplying out this negative 16 with 1 by 15. So we can get here negative 16 by 15. Reason for doing this is now that we can add our individual 2 by 5 with this negative 16 by 15, and then we will get our final values. So now that we know this, we can just do 2 by 5 minus 16 by 15, which is equal to negative 2 by 3. Now we have the value. Now we just need to write a final answer. So our final answer, instead of writing small f of x, we write a larger f of x, capital F of x. And capital F of x equals to, let's write that entire equation now. Okay, we have here okay, so in PDFs we have 0 otherwise. In CDFs we have 0 and we have 1. 0 happens when the value of x goes below the range. 1 happens when it goes beyond the range. How this works is because our range over here is between 0 to 5, 0 to 5. These two functions spread across 0 to 5. So when x is lower than 0, we get a value of 0. So let's put this here, when x is lower than 0. And when x is greater than 5, we get the value of 1. So x is greater than 5. And right here, we can write our values here. We have x squared over 10, x squared over 10. That range applies from 0 to 2. But ensure that our inequality symbols remain the same. We cannot afford such silly mistakes. Next up, we can have 1 by 15, which is factorized. You have here 10x minus x squared minus 2 by 3. And we have values from 2 to 5. And this sums up CDF. Now find the median value of x. What does it mean to find the median value of x? So to find median values of x, it involves integrating from the PDF. And while this may seem a bit difficult, it's rather quite simple. That's why it's only available for 2 marks. So to find this value, firstly you should know that this value of m is between 0 to 5, such that when you plug in this value into the CDF formula, it yields you the answer of 0.5. okay, so that means that when you plug this in the formula f m, it will be equals to 0.5. So that means that m is between 0 to 5. Right. So let's first see which range it applies from. Is m from 0 to 2 or 2 to 5? Based on this, our next calculations will proceed. So using the CDF of the first from 0 to 2, you get x squared over 10. The maximum value x can be is 2. So we're going to put over here 2 squared over 10 equals to 4 by 10. And that means that 4 by 10 is the maximum that the first function can cover. So we know that it has to go and reach the second function because the fm is 0.5. So if I was to, if still do not understand what this means, if I was to represent this in like a small bar where the lowest is 0, highest is 1, our first function, which is x squared by 10, covers only 40% of this entire thing. Covers 40% or 4 by 10 of this. This is how much the first function covers. That means the second function covers the rest 6 by 10. But we only want to know the value at which our second function covers 50%. So that means our second function should only be covering 0.1. A certain value m in our second function gets you 0.1. But we cannot directly use this CDF formula. Reason being so is because we included f2 over here to get the CDF formula. Right now it's not going to be too difficult. It should rather be quite simple. Okay, yeah. So what we have here, we just need to get this part of the formula. We just disregard f2. Okay, so we have this part of the formula. This is all we need, this region right here. So basically all we needed to do is integrate. All you need to do is integrate the first formula here with respect to m, however. Okay, so we need to integrate with respect to m. So we can just write this process down, but there is no chance that we'll make an error because our first one seems to be right. So let's integrate with respect to m. The first equation was 2 by 15 with integration of limits m 2, and this is for the equation 5 minus x. Notice how we don't need a dummy variable again, because this time we are doing it with respect to m, the upper limit, and we differentiate with respect to this. So like how we had t over here and x over here for the previous one, we can replace our exact answer like this. So we get here 1 by 15, 1 by 15 multiplied by 10m minus m squared minus 16, right? And this is what we call our second function. Okay, so this second function, yes, so this second function should yield us 1 by 10, because the first function covers 4 by 10 of it, and we already considered f2. When we considered f2 over here, we don't need it for our second function because it's being calculated here. f2 was 4 by 10, so our second function should not include the calculation of f2. And when we have 4 by 10 here, which is what's covered by the first function, our second function would cover just enough to get to the 0.5, so it will be 1 by 10. Now let's multiply each of the sides with 30, because that's the LCM of the denominators of 15 and 10. So we get here, if we multiply, you get 10 minus m squared minus 16, and this will be equal to 3. Now let's simplify this further. We get 20m minus 2m squared minus 32, and this will be equal to 3 again. And now we are coming to the quadratics part of this. This is the simpler part. We can bring in, I'd like to have the highest degree in a positive constant, a positive coefficient. So we can bring everything to the right side, and we get 2m squared minus 20m plus 35. And this will be equal to 0, because now that we've equated it, we got it equal to 0. And how do we solve this from now? We could use the quadratic equation, but you have to understand that will take up some time. So what we can do here is go to our calculator menu, and the settings here I think are written in German, but in yours it should probably be English. And over here, right here where it's labeled A, it should be labeled with equation slash function. Over here we have to choose between simultaneous equations or polynomial equations. We're doing polynomial, and with degree 2, because it's m squared, which is the maximum limit. So we have here, we can plug in our value 2, negative 20, 35. It's a big time saver. And our values for m will be 10 plus root 30 by 2 or 10 minus root 30 by 2. But only one value of m will satisfy. The only validation technique that we can use here is the range check. And in this case, the range is between 0 to 5. But we narrowed it down that m can only take up a value from 2 to 5, because when we plugged in the value of 2, it only covered 4 by 10. So we know that the m value is between 2 to 5. This value satisfies it, 10 minus root 30. However, the value right above us, which is this here, 7.74, this value does not come in that range. So we take in 2.26. So we write here m equals to 2.26. If they didn't write an exact form, if they gave exact form, then we'll have to write it in this way, 10 minus root 30 by 2. But they're asking what's the median value. We don't need to write that. Finally, find ex squared. Okay, this is also another simpler one. So for the first equation, it was 1 by 5x. So now when we have to integrate, okay, so integrate with respects to the limit. The range is from 0 to 2. We have our limits 0 to 2. No substitution of the upper limit. And over here, we have 1 by 5x. When we are having to find ex squared, we have to multiply the entire thing with what's inside the bracket. In this case, x squared. So 1 by 5x times x squared would be 1 by 5x cubed. So we're integrating here x cubed with respect to dx. This is added on with the integration of 2 by 15 times, for the limit of 5 to, we have here x squared times 5 minus x. Just like the previous one, we have to multiply x squared with both. Now we just need to integrate with respect to x. So the first one, let's integrate this in parts, and this will be equal to e of x squared. Okay, let's leave that be. So for the first one, once we integrate, we get here we get 1 by 5 times 1 by 4 x to power 4 with limits 2 and 0. Now you know that when you plug in the value of 2 in here, we get 1 by 5 times 1 by 4 times 2 to power 4. 2 to the power of 4 is 16. So that means 16 over 4 gives 4. So we have here 4 when you plug in. And we subtract that when we plug in the value of the lower limit, which is 0. 0 to power 4 times 1 by 4 is 0. So we can close our bracket and leave it be like this. And therefore our first value when integrated with our limits is 4 by 5. So now we need to add 4 by 5 with this integrated value and substitute the limits. Okay, how we do this? So we have 2 by 15 as our constant that we integrate with. And once you integrate x squared times 5 minus x, you can just simplify this. It's 5x squared minus x cubed. And we've already integrated x cubed, so that should be simple. To integrate 5x squared, we can just add up one exponent to our x squared, we get x cubed. And x cubed, so 3 times 5 by something is equal to 5. That means that something is 3. So our fraction here is 5 by 3. And you can just confirm this by differentiating and seeing if it is equal to 5x squared. In this case it is. And we can put here x to power 4 whole by 4 with limits 5, 2. Let's substitute these limits into our calculator. So for the first one we have 5 by 3 times 5 to power 3 minus this with with x to power 4, which is just 5 to power 4. Divide that with 4, right? And that makes up our upper limit. Now we subtract that with our lower limit value. So 5 by 3 times 2 to power 3 minus 2 to power 4 whole divided by 4. And this is what comes in inside a bracket, which is equal to 2 by 15 times 171 over 4. So let's multiply this to get a fractional value. 15, we get here 57 over 10. Now our final values. So we had to integrate the two values and then add up together. We have 4 by 5, 57 by 10. So let's add up the two values. 57 over 10 plus 4 by 5 equals to 6.5. It's actually 65 by 10, but we can take it as 6.5. They would want it in integer values, in decimal. Find the probability that x ranges between 1 to 3. This is by far, I think, the most simpler equation. So we have here, there is a formula. So when we have x ranging between a to b, the probability of x ranging from a to b is equal to the CDF when you plug in the value of b minus when you plug in the value of a in CDF. Right? So using the formula above, we can note that f of 1, in this case the lower part is 1, f of 1 equals to, now 1 falls in the first equation's range because it's between 0 to 2, so you use 1 square by 10. So you have here 1 over 10. Now we have to go for f3. f3 is equal to, f3 falls in the second equation part. So when you plug in the value of 3 into this entire equation, this equation right here, we get 1 over 15 times 10 times 3 minus 3 squared whole minus 2 by 3, which is equal to 11 by 15. 11 over 15. And so our final value would be f3 minus f1, which is basically meaning 11 by 15 minus 1 by 10. So 11 by 15 minus 0.1, which is equal to 19 by 30. And that right there is the final value, 19 over 30. That sums up all of CRV. Now we have PGFs. So to find the PGF of y, which is a sum of two independent observations of x, you should know that gy of t is equal to two independent observations, sum of two independent of x, which means we're doing gxt multiplied by gxt, which is gxt the whole squared. That's the first thing you want to know. Second thing you want to know is that you want to factorize this. Right, we need to factorize this to make our calculation simple. We can take 1 by 10 out of this entire thing, 1 by 10t. When you factorize 1 by 10t out of this, we get 2 plus 5t plus 3t squared. The reason why we factorize is I'm going to show you right now. So this is gx of t. Now it's going to be easier for us to multiply our two gx of t values. Sure, lesser steps would be to do with decimals, but we are less error prone with this method. So 1 by 10t times 2 plus 5t times plus 3t squared, and this is multiplied with same thing over again. It's basically squared. It's like that. 40 plus. Okay. We can multiply what's outside the bracket, which is 1 over 100t squared, and inside we can use FOIL method for these two. We need to multiply these two values here. So we get 2 times 2, which is 4. Then we can multiply with 5t, which is 10t. Then we get 6t squared. And now we can move on to 5t. 5t times 2 is 10t. 5t times 5t is 25t squared. Yeah, and 5t times 3t squared equals to 15t cubed. Okay, now that we've got those ones, now we need to multiply with 3t squared with each of these, which is equal to 6t squared plus 15t squared t cubed plus 9t to power 4. Okay, now we just need to simplify each of these. We get 1 over 100 t squared multiplied by our integer value is 4. Our value of the coefficient of t is going to be 10 plus 10, and yeah, I think it's just going to be 20. Let me see. Yep, 20t plus the coefficients of t squared, which is 6 plus 25 plus 6, which is 37. And this 37t squared is added on with our coefficients of t cubed, which is 15 plus 15. That is 30 t cubed. Next we have to add with our coefficients of t to power 4, which is 9. But this isn't our simplified answer just yet. So now to write our final answer, remember, factorizing and all, they're not essential steps, they're just simpler steps. If they give you your gxt in decimal, they expect our and unfactorized, they expect our final answer for gy of t also to be in the same manner. So this is a simplified form that can be used, that it's much easier, but we need to write this in decimal. So when we write it in this decimal, we need to multiply 1 by 100 and t squared. So we get here 0.04 t squared plus 0.2 t squared t cubed plus 0.37 t to power 4 plus 0.3 t to power 5, finally 0.09 t to power 6. Remember, we're just simplifying each of these, we're just multiplying each of these with this. However, we will use this equation for any kind of differentiating or multiplication purposes. Find ey and variance of y, which is going to require differentiation, as I said earlier. To find ey, okay, I'm going to write down two formulas. So ey equals to the gy differentiate when you plug in the value of t, and then you have here vary. This is equal to gy double differentiation and plug in the value of t as 1, add that with ey, which is the same as gy dash, and then we minus that with ey the whole squared. Right, so you can plug in this value right here, it wouldn't matter, both ways are it's going to give the same value. So right here we need to find the differentiated function of y, pgf of y. That will be equal to, let's differentiate. So we have here our equation. So 0.04 times 2 is going to be 0.08 t. This is added on with our next one, which is 0.2 times 3 t squared plus 0.37 times 4. I think that is calculator for, and we have here 1.48 t to power 3 plus, now we have 0.3 times 5, which is 1.5 t to power 4, and finally 0.09 times 6, which is 0.54 t to power 5. Now to find ey, it will be to plug in t equals 1. So when you plug in t equals 1, it doesn't matter what degree the polynomial is in. If it's 1, 2, 3, 4, 5, it doesn't matter. 1 squared, cubed, 4, all of it will still be equal to 1. So all we need to do is add up all the coefficients here. So it's going to be 0.08 plus 0.6 plus 1.48 plus 1.5 plus 0.5. Essentially what we're doing is plugging in the values of t with 1. Okay, and when you do that, you get this result here, which is 4.2. This is our e value, and hence, given that they have asked us to find ey, it is nice that we first box our answer for ey, just to make it clear that we found ey equals to 4.2. But this isn't too essential, because without ey you can't find a correct value for variance. To find the variance, we found out a double differentiate of gy. So to find the double differentiation of this, we're just going to repeat the process. That's going to be 0.08 itself, no t, plus 0.6 times 2, which is 1.2 t, plus 1.48 times 3, that's going to be 4.44. Moving on, we have 1.5 t to power 4. Differentiate that, it's going to be 6 t to power 3. And finally we have 0.54 times 5, which is equal to 2.7 to the power t over 4, t to the power 4. Now when you plug in t equals 1, let's actually put this here. So when we have here gy double dash, when t equals to 1, we get 0.08 plus 1.2 plus 4.44. Once again, degrees of polynomials don't matter when you're plugging in the value of 1, plus 6 plus 2.7 is equal to 14.42. So now that we found this, now the next step is quite simple. This isn't our final answer, of course, because using the formula here, we just need to write variance of y is equal to gy dash dash 1, so it's 14.42, minus that with, no wait, plus that with 4.2, which is our ey, minus that with 4.2 the whole squared. So to get this value, we get here 0.2 plus 4.2 minus 4.2 squared, which is equal to 0.98. Hence we can also box our answer for this one. What just happened? Okay, variance of y is equal to 0.98, and that's our variance, and that sums up all of PGF. Going back to inferential statistics, okay, so there are two colleges A, B competing in computer games challenge. Time taken for a randomly chosen student from college A to complete the challenge has a normal distribution with mean as mu. The time taken, x minutes, are recorded for a random sample of 10 students chosen from college A. The results are summarized as follows. The total sum is 828, total sum squared, total values when you square it is equal to 68622. The test is carried out with 5% significance level and supports the claim that mu is greater than k. Find the greatest possible value of k. Okay, first of all, we need to, whenever we do an inferential statistics kind of test, we have to state our null and alternative hypothesis. In this case, our null hypothesis would be mu equals to k, and our alternative hypothesis. Okay, so whenever we have a test where it compares two means, just remember H null is always going to be mu equals k, and the second one, which is alternative hypothesis, will always support something against H1, so it can be greater, lesser than, or not equal to. Right. So for the alternative hypothesis to be favored in an inferential statistics based question, you have to know that the critical value must be lower than our test statistic. Okay, a critical value must be lower than test statistics, so that means we're going to have an inequality based answer, or in this case, yeah, inequality based answer. So let's put this here. First thing we need to know is to calculate the test statistic, so we need to calculate first unbiased estimate S2 of x, which is equal to 1 divided by the number of terms of x. Alright, I need to write number of terms of x equals to 10, and the mean of x, sample mean x, equals to 828 by 10, which is 82.8. Right. Okay, moving on. We find the S2 of x is going to be 1 by nx minus 1 multiplied by sum of x squared minus sum of x whole square that divide that with the number of terms of x, and this will be equal to 1 by 9 times 68622 minus 828 the whole square all divided by number of terms 10, and this value is going to be 116 over 15. So this is the value that we use in our calculator for our calculations, but what Cambridge expects is a decimal based answer that is rounded to at least 4 significant figures. Let's keep it to 7.067. Okay, now that we have our values, next thing we need to know is that if our test statistic should be represented with letter Z or T. In this case we have 10 students, that means degrees of freedom equals to 9. As you can see in the critical values over here, there is critical values for 9 over here, but that means that we need to represent our letter with T. So T is equal to, okay, yeah, T is equal to sample mean x, so that is going to be 82.8 minus mu. Mu is represented as k as stated in our hypothesis. Mu equals k, so sample mean of x minus k whole divided by yeah, this is whole divided by our unbiased estimator S2, which is 106 over 15 divided by 10, so that means it's 106 over 50. And this value right here, this is our T value, so let's just erase this, won't be necessary, right? And this T value is going to be greater than our critical value, greater than or equal to actually, because when our critical value is just lower than, that means that it's going to be accepting H null. But if critical value is equal to or greater, if the critical value is greater than a test statistic, the H null is supported. But if critical value and the test statistics are both equal, that means that we are supporting H1, which is alternative hypothesis. Our critical value, given that this is a one-tailed test, we are looking at every value in which k is lower than mu. Okay, we're not looking for higher, so we're looking at only one side. That means it's a one-tailed test. For a one-tailed test, the formula was 1 minus alpha by 100, where alpha is 5. That means that our p value will be 0.95. For degrees of freedom 9, that means our critical value is 1.833. 833. This 1.833, okay, let's root the values and multiply this with 1.833, right? So that we have here, when you simplify it a bit more, it's going to be greater than or equal to 1.541. And now we can put add k in both sides and subtract 1.541 from both sides. So if you subtract 1.54 from both sides, you get 82, you get 81.3. We can keep it at 3 significant because it's an answer. And when you're adding k on both sides, k comes to the right side, so k must be lesser than or equal to 81.3. This is a value for k. Next up we have for B, a random sample of 8 students is chosen. So there are some data that we need to write first. The number of terms is equal to 8. The sample mean for Y, which is equal to 79.8. Next we have unbiased variance estimate. This is S2Y. This is equal to 9.9 0.66. Okay, so these are all the values that we have here. Using a 2-sample test at the 5% significance level to test whether the mean time of students B is the same as mean time for college A. So when we're testing, we always have to write our hypothesis. Let's represent this in a different ink. Let's put blue as last time. Okay, yeah. So H null states that the population mean of B is the same as A. However, now they're saying that given that they're saying that it's the same time as A and B, that means H1 means that mu A is not equal to mu B. They're not saying that mu A is greater than. Saying it's just not equal to mu B. Okay, now once again we can use our basic knowledge of statistics. First of all, there is one important part that you should not miss out. It says that they have the same population variance. When I referenced the kind of question that we had last time, I remember saying that we need to use pooled estimate whenever we have the same population variance. So yes, that applies over here. We use S2P, not just S2. Therefore, our equation changes into this S2P. This is called pooled estimate, and this is equal to the S2 of X times degree of freedom of X plus S2 of Y times the degree of freedom of Y whole divided by number of terms of X plus number of terms of Y minus 2. The reason we put minus 2 is because that's the number of parameters estimated, and that is equal to S2 of P. And now we can just plug in each of our values because we have every one of the values here. S2 of X was 116 over 15. Let me test that right there. Okay, 116 over 15. We multiply this with our degrees of freedom of X. Number of terms is 10, so degree of freedom is 9. S2Y is going to be 9.966 times degrees of freedom, which is 7. Degree of freedom meaning number of terms minus 1. So number of terms for X was 10, Y was 8 and minus 2, and we have here 8.335. We're going to take it as exactly 8.335 because it's 4 significant figures when we compare the values. Yeah, but this won't matter too much because we're going to be using this in our formula. So how you depict it over here, just to show Cambridge that you know that you've calculated the value for S2P. This is nowhere going to be compared. So we just need to plug this into our equation. Right, so in this one we have total of 10 samples for X, 8 samples for Y. Our degree of freedom will be 10 plus 8 minus 2, which is essentially the denominator of our pooled variance. So 10 plus 8 minus 2 is 16, and therefore we have a value over here. It can be any one of these 9 values. That means that we have to use the t distribution. Therefore our test statistic will be depicted with the letter t. T is equal to mean X minus mean Y whole divided with the root of S2P multiplied by the root of 1 by number of terms of X plus 1 by number of terms of Y, and that makes up our entire equation. We have every single one of these values. All that's remaining is to plug in these values. So we have here mean of X, sample mean of X was 82.8, sample mean of Y was 79.8 if I'm not wrong. Yeah, and our pooled estimate was 8.335. I put that in answer, and we multiply this with number of 1 by number of terms of X plus 1 by number of terms of Y, which is number 8, and therefore we have 2.191. 2.191. That is a test statistic. Now to find our critical value. So critical value, we can reference this by writing T. For T distribution, we write T bracket, we write degrees of freedom, which was 16 as calculated before. And since we are doing a 5% significance level, a two-tailed test, because now mu a can be greater than, lesser than, or equal to. So we're looking at both sides, right? Since we're looking at both sides of the place, it can be a 5% significance level test. For a 5% significance level, we divide alpha with 2, which is 2.5. That means you just do 1 minus 2.5. So let's write 1 minus 2.5 will be, sorry, 1 minus 0.0025. So that will be 0.975 here, and our critical value is 2.120. Therefore our alpha will be 0.975 and our critical value is 2.120. Now we compare the two values. Although close, it is clear which one is bigger. And 2.191. You can see that the test statistic is bigger. So when test statistic is bigger, we reject H null. And so our answer would be, whenever we reject H null, it's going to be there is sufficient evidence to suggest that college college A and B do not have the same mean time. That should be our answer for this one. Next up we have non-parametric tests. A biologist studying the effect of nutrients on the heights to which plants grow. A random sample of 24 young similar plants is divided into two groups of A and B. Okay. Plants in A are fed with nutrients and water. Plants in B are given only water. After 4 weeks, the heights in centimeters. Each plant is measured and results are as follows. The biologist decides to carry out a test at a 5% significance level to test whether nutrients have resulted in an increase in growth. She carries out a Wilcoxon-Ransom test. Why is this an appropriate choice of test? Okay, this is rather simple, because we could normally carry out a Wilcoxon matched pairs test, but we do not carry a matched pair test. Why? Because they're saying 24 young similar plants. So there is nothing to distinguish this group of 2 from this group of 2. And that makes all of this indistinguishable from each other. Therefore, they possess no unique kind of characteristics to match them up together. Hence, the only test that does that for non-parametrics, and it's quite accurate, is the rank-sum test, Wilcoxon in particular. So we can write over here that so in what I've just said right now, we can say that the differences for the populations are not assumed to be normal. It could be normal, but it's not assumed anywhere in this question. Are not assumed to be normal. Okay, carry out the Wilcoxon-Ransom test for these results. Very simple. So yes, Wilcoxon-Ransom test. We have to ascending order. We don't have to do this, but you can. And therefore I'm going to do it, and we will ascending order all these values. So I get 10.6 is the first one. Next value was 11.1, 11.8, 12.0. Next we have 0.1, 2, 3, 4. 12.1, 12.2, 12.3, 12.4, and then we have 13.2, 0.5, 0.8, 0.9. 13.2, 13.5, 13.8, 13.9. Let me just fix this. Okay, so I have arranged the first part in ascending order. Now the next part also needs to be in ascending order. This is going to be starting with 10.5, 0.7, 0.8, 0.9. Okay, 0.5, 7, 0.8, 10.9, 11.0, and then we have here 11.2, 0.3, 0.6, 0.7, 9.9, 11.2, 11.3, 11.6, 11.7, 11.9. So that means that we should have two more values remaining. It's going to be 12.5, 12.6, 5, 12.6, and this right here is our ascending order ranks. Now before we do the ranking, we need to state our null and alternative hypothesis. So our null hypothesis is going to be population medians are not equal. Whenever we have Wilcoxon rank sum test, we always refer to medians, and I'm going to write this in letters. So MA, and it says that biology deserves to claim whether the nutrients have resulted in an increase in growth, which means has this happened, has A become greater than B, and because A is the one that's fed with nutrients and water, so that means that our null hypothesis that always stays that they are equal, and our alternative hypothesis will just combat that, but what the researcher says, MA is greater than MB, and that should be our hypothesis stuff. Next up we will start ranking. Very simple one this is. Given that we've already ascended order, we can put 1, this is 2. What I'm doing is I'm arranging these numbers, these 24 numbers, in order. We already done in ascending order. Now we need to label them with numbers 1 to 24, where 1 is the lowest and 24 is the highest. So 1, 2, this becomes 3, 4, 5, 6, 7, 8, 9, 10, 11, this becomes 12, 13, 14, 15, 16, 17, 18, these last two become 19, 20, and therefore these must be 21, 22, 23, 24. 4. Now we can just calculate the total of all these ranks. So for the first one is 1 plus 7 plus 12 plus 14 plus 15 plus 16, 17, 18, 21, 190. Let me check if I've done everything right. 14, 15, 16, 17, 18, 21, 22, 23, 24. Yeah, good to. This is going to be 190, so let's just write the cumulative. And over here we have, oh I see, yeah, I made a mistake in the ranking. This should be like this. Yeah, now that means that this should be 191. Okay, and now the total of this, right? Total of this would be 1 plus 3 plus 4 plus 5 plus 6 plus 8 plus 9 plus 10 plus 11 plus 13 plus 19 and finally plus 20, which is equal to 109. Now our test statistic T is equal to the minimum of 191 and 109, which in this case is obviously going to be 109. Now, given the fact that we have 12 samples and that in the Wilcoxon rank sum test we don't have for m equals 10 and n equals 10, we need to use these things right here. These things are essential. So mean is equal to 1 by 2m and all those formulas. So when we are associating with that group, we need to know that there's another formula. This formula is quite important. So z is equal to the test statistic t minus the expected value plus 0.5 whole divided by sigma being the standard deviation. And to calculate E, which is just basically sigma squared and whole root, which is the variance, and to calculate E here, E will be 1 by 2. M is the number of samples of the first group, which is the lower number of group. In this case both are equal, so M can be 12, it doesn't matter. So 12 multiplied by 12 plus n being the other 12 plus 1, which is equal to 150. Next we have our variance, which is sigma squared, and this is equal to 1 by 12 times 12 times 12 multiplied by 12 plus 12 plus 1, which is basically 12 times 25, which is 300. Now we can plug in these values into our equation. So that means that z is equal to t value is 109 minus expected value of 150 plus 0.5 whole divided by root of 300. This gives us negative 2.338. We keep it to 4 significant figures for this one as well, and this has a very good reason why. It's because now we need to calculate the probability of z. What this means is that we're going to be using normal distribution, which is right here. To calculate this, we need 4 decimal places to be absolutely precise. So that means that we need first to calculate the probability of negative 2.338. Okay, calculate the probability of negative 2.338. It will be equal to 1 minus the phi, I think it's called phi, of positive 2.338. So first we'll calculate what is positive of this, and to find 2.338, the positive of that, I'll teach you how to read this table. So firstly it's going to be 2.3, that means our row is this one. Next we have the second decimal place, which is 3, so 2.338. so 3 is going to be here. We're going to have 0.9901. I will plug this value in the calculator, 0.9901, and this will, and now 8 is added on to the last part, 8 here, 2. What this 2 means is that you're adding 2 to the very last digit. So we're going to add 0.123 2. So we have here 0.9903. And what is this equal to? Well, 1 minus of this answer will get 0.00097. 0.0097. Now this value right here, 0.097, we have to now compare it with our critical value. In this case, our critical value will be the percentage itself because it's a probability kind. And we are carrying this out at 5% significance level. 5% is 0.05 in decimal. And this 0.05 is greater than this. And whenever the critical value is greater than the test statistic, we normally accept it. But in non-parametrics, we reject. So we have to reject H null. Normally we don't see these many rejections of the null hypothesis in a paper, so it's quite weird. And so we say that there is sufficient evidence to suggest that nutrients play a part in the growth of the plants. And that right there sums up our paper. I think yes, it does. That has been Further Mathematics Probability Statistics 4.3 of the May-June series of 2020. Thank you for watching. Hope you enjoyed, and see you next time.